Hey students, we're going to talk about section 15.3, which is buffering capacity. This is a really important part about how buffers work and how we would select buffers that are going to work the best to maintain a pH that we want. So buffering capacity references the amount of protons, H plus, or hydroxide ions, that a buffer can absorb without changing the pH by very much. Now, one of the ideas we've seen with our calculations in the other sections is if strong acid is added, so if H plus is added, the pH will go down a little bit. And if hydroxide's added, the pH will go up, but it's by a small amount. And that's what this buffering capacity is exploring. One of the important parts is the more concentrated the buffer components are, the better the buffering capacities. So we want buffers to be made with high concentrations of the weak acid and high concentrations of the conjugate base. And so the other part, though, is going to be what ratio of those is going to make for a better buffering capacity. So that's what we're going to explore in the next few slides. To do this, what we're going to do is we're going to do some calculations so that the numbers can show us. So here's acetic acid. It's at a pretty high concentration of 5 molar acetic acid and 5 molar sodium acetate. So that's our A minus. Excuse me, and the weak acids are HA. And then this has the pKa of 4.74, negative log of Ka. So I'm hoping by this point in your studies that I don't have to keep showing where I get a pKa from, that you know that it's the negative log of Ka and that you can quickly calculate that. Okay, so we have this buffer with both of these components. And so in our container, we have weak acid and conjugate base. Can I ignore Na plus because it's just floating around a spectator? And now to the buffer, I'm going to add HCl, which is a strong acid. The important part is going to be the H plus. So the question is going to be, if we're adding a strong acid to a buffer, which buffer component will react with it? Acids don't react with acids, so it has to be the base. So the base is going to react with H plus to neutralize it. So the amount of acetate is going to go down in the buffer and the amount of acetic acid is going to go up. So now the question is going to be, by how much? Okay, so that's what we're going to explore with the next calculations. Okay, so initially, the pH of this buffer, if these are both 5 molar, hopefully you're understanding that if the buffer ratio is 1, where these two cancel out, pH equals pKa. So the pH will equal the pKa, which is 4.74. That's where we're starting from in the buffer. Okay? And now we've added H plus. So we have all these things floating around in there. We have the weak acid. We have Na plus spectator weak base, H plus and Cl minus from the HCl and water. So the base will react with the H plus. So I had already written that on the previous slide. So there's going to be neutralization. So what this then is set up, this is stoichiometry. That we start off with 1 liter of this buffer at 5 molar base, 5 molar weak acid, and we add 0.010 molar of H plus. And what's going to happen here is that the strong acid is our limiting reagent because it's less. And so after reaction, all of that's going to be consumed. So you end up with 0 strong acid, and you're going to react off 0.010 molar of the base, and then you're going to form 0.010 molar of the weak acid. So now they're not 1-to-1 anymore, right? Now you have 4.99 of the base and 5.01 molar of the acid. So let's see what that's going to do to our numbers. Plugging back into Henderson-Hasselbalch, this is the new numbers. 4.99 for the base and 5.01 for the acid. And if you notice, because that change was so small, the pH still equals pKa. That's a really great buffer. And what made it great was that we started with really high concentrations of weak acid and base, but not only that, the ratio of A minus to HA was 1. So those are our two main points. We want high concentrations of HA and A minus, but that enough doesn't mean we're going to have a great buffer. And we want them to be as close to each other. We want the ratio, and I'll put it as that ratio. We want this ratio of A minus to HA to be as close as we can get it to 1. That's going to make for a really great buffer, because then when you add a strong acid or a strong base, the change here is very small, and the pH stays around the pK. So this is a really important slide to understand as far as the numbers. To prove this to you, let's look at the same buffer, but with smaller concentrations. This all says the same thing, so you can look at that more slowly. Same thing that I said there. Okay, so it's known then that a pK for weak acid should be as close as possible to the desired pH. And what would be the problem if you didn't do that, or if the ratio wasn't as close to 1? Then it wouldn't be a great buffer. Okay. All right. So this next question is asking you want a solution at pH 4.30. What buffer system will you do? Your book does this, in my opinion, in a really difficult way. So I would just like to do it in a very simple way, which is that we have the Ka, so we would simply find the pKa's, negative log of these numbers. Again, won't be showing that right now because you should be able to do that part. Okay, so I'm looking at these numbers. Which one's closest to 4.30? pKa is our benzoic acid. So this would be our appropriate buffer system because it's closest to the desired pH. And trust me that you're going to be using this in a lot of upper division lab work if you're going into biology or chemistry. So biologists are going to ask you in their microbiology labs, in their physiology labs to think about what buffers you're going to use for experiments. So this is a concept that hopefully you'll take with you. Okay, the second part of the question that they asked was calculate the ratio of, well, they wanted as HA over A minus required for each system to yield a pH of 4.30. We already determined which system was going to work the best. But if I want to know the ratios that are going to work best, or I want to show you that they're who's closest to 1 essentially, because remember, buffers that the ratios closest to 1 are going to have the best for that system that we need. So I'm going to click on this. This is how your book did it. I want to kind of change this up just a little bit. We wanted a pH, so the desired pH .30, and then I had written on the previous slide the pKa for each of these. Okay, so let's take a look at that ratio that's important in Henderson-Hasselbalch, which we talked about in the previous video lecture. How do I solve for A minus to HA? Would be 10 to the pH minus pKa. So if I go down the line, the reason why I don't like, well, I wouldn't say I don't like, but you see that all of this here, this is using the Ka expression, which I think is more work than this top one. So this is an or. You can use the way I'm doing it with Henderson-Hasselbalch or use Ka expression. I personally believe Henderson-Hasselbalch is much easier. So if I go through and find the ratio of A minus to HA for each of these, I'll do the first one. Actually, let me look at the benzoic acid one. So I'm going to star this to be this guy here. 10 to the pH that we want, 4.30 minus 4.19. Let's see what ratio we have in this buffer. I'm going to grab my calculator. .3. Now go ahead and try the rest of these to see what ratio you're getting for each of them. And what you're going to notice is that the other ones, the ratio is really farther from 1. So that's why this buffer system of benzoic acid was our best choice for this pH. Now, one last thing before we wrap up is this one asked for HA over A minus. Notice that this 0.78 is not the 1.3. If you notice, it's the reciprocal of that number. They had asked for the buffering, or they were discussing it, the inverse of that. Regardless of which way you want to look at it, the ratio that we want for the best buffer system will be closest to 1. I guess before I stop talking, let me just do one more for you so you can see how different. So let's take the top one, which is really far away from our desired pH. So if I take this ratio for the 2.87, that would be 10 to the 4.30 minus 2.87. That's a buffer ratio of 27, A minus to HA. And then 1 over that is HA over A minus. So that is really far from a desired buffer ratio of A minus to HA of 1. Okay, so to recap, the two important things that you want when selecting a buffer is you want the ratio of A minus to HA to be as close to 1 as possible, which means that your pH will be near the pKa value. And then you want high concentrations of weak acid and conjugate base.